Now we're still talking about Taylor series, but we want to talk about a special kind of series called the binomial series. Now, we already know that from algebra that 1 plus x quantity raised to the power of p, this will end up being a polynomial of degree p. Matter of fact, the expansion of this binomial would be, well, the very first term will be 1, but we can write it as p choose 0, that's the number 1, plus p choose 1, and then this term would be your first degree term, so x to the first power. Your next term will be the second degree term, so you're going to have an x squared, but the coefficient would be p choose 2, x squared, and so forth, plus etc., until you get to p choose p. And then this last term, that will actually give you just, this will give you the number 1. And then this will be x to the power of p, right? The highest power of your variable, where all of these are your coefficients, right? This is, if you remember from your algebra studies, this is basically the expansion of the binomial theorem. You also have Pascal's triangle that helps you get these coefficients as well. But we can define it as the following. All of these coefficients can be defined as the following. P choose k is defined to be p times p minus 1 times p minus 2, and you keep on going, right? P minus all the way to minus k plus 1 all over k factorial, like that. Very good. And remembering that p choose 0 is just equal to 1. You know, in algebra, a lot of times we have another way of writing this, just kind of like an FYI. This can be rewritten as p factorial over k factorial times p minus k factorial. That's another way of writing what we just wrote up here. Okay, so this is just an alternative way of writing it. In addition to that, Pascal's triangle gives you, I'm just writing down Pascal's triangle, gives you the coefficients that we're talking about. And of course, you can keep going with Pascal's triangle. This would be, this first row would be corresponding to the power of 0. And this is row 1, which would correspond to the power of 1. This right here, this p, power of 1. And then this is degree power of 2. And then this is the power of 3, and so forth. Remember that Pascal's triangle, every row begins with a, let me see if I can move this. Every row begins with the 1, and then you add the coefficients. 1 plus 3 gives you 4, and then 3 plus 3 gives you 6. 3 plus 1 gives you 4, and then every row ends with the 1 as well. So these here would be the coefficients that correspond to a binomial being raised to the 4th power, okay? The next row, I'll just do one more row. 1, 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and always begins and ends with a 1. And you can keep going, of course, depending on what your p-value is, depending on the power to which you want to expand your binomial, okay? For example, let's just do an example really quickly. If I have a binomial 1 plus x and I want to raise it to the 5th power, then it would be 5 choose 0 plus 5 choose 1. And then I didn't mean to write this fraction bar right here. I don't know where that came from. X to the 1st power plus 5 choose 2. I did it again. 5 choose 2. And this is x squared plus 5 choose 3. X cubed plus, I have to go to the second row here, 5 choose 4, x to the 4th, and then this will be my last term, 5 choose 5, and then x to the 5th power. This is how this would expand. Now, if you look at the 5th row of Pascal's triangle. Basically, look at this row right here. Those numbers are the coefficients of this expansion. But you can also get these coefficients by using this expression here, okay? Or this one right here in red, either way. But at the end of the day, this would be equal to 1 plus 5x plus 10x squared plus another 10, this time x cubed, and then plus 5x to the fourth, and then plus 1x to the fifth. Okay, so that's how that would expand. You can see how beneficial this is because we can get the expansion of a binomial like this, fairly quickly. Now in algebra, we always called, let me come back up here, we always called this power here in algebra an integer value, a positive integer, so a whole number, okay? But we would like to extend that, that idea now and say that P now just represents any real number, not zero, but any real number, all right? The result is a Taylor series called the binomial series. All right, so here's the formal definition for the binomial series, all right? So let me see if I can move all this up and I'll get it written for us. So here's the definition, the formal definition for a binomial series. For real numbers, P, so in algebra we said this is some natural number, right? Some whole positive number. But now we're just saying let it be any real number, just not zero. This is a Taylor series centered at 0, but we call it the binomial series. It's 1 plus x raised to the power of p. We can write it this way in summation notation, where p sub k, not p sub k, p choose k, excuse me, p choose k are the coefficients of the expansion, and x to the power of k are the variable parts of each term. Now, if k is 0, then this is p choose 0, which is 1, and x to the 0th power, which is 1, which is why the first term is just 1. And then if k is 1, then this is x to the first power, which is just x. That's why that's just x. And if k is 1, then this is p choose 1, which is just going to give you p. All right? Notice the pattern. Notice that the denominator is 2 factorial, so then you have 2 factors up here, p times p minus 1. This is 3 factorial, 3, the number 3, there's 3 factors, p times p minus 1 times p minus 2. So the next term, the denominator would be 4 factorial, so the numerator would have 4 factors, p times p minus 1 times p minus 2 times p minus 3. Of course, the pattern for the variable parts, this is x to the 0th, x to the first, x to the second power, x cubed, and then x to the fourth, x to the fifth, and so forth, which is why it's called a power series or a Taylor series. Okay, this series converges for this interval of convergence here, and possibly at the endpoints, depending on what p is. Now, if p is a non-negative integer, that means if it's a whole number, the series terminates and results in a polynomial of degree p, okay? Just like we saw in algebra. All right, let's find the first 4 terms of the binomial series for this square root function centered at 0. Okay, first, please notice that the first term is always 1. Okay, and you know why? Because when k is 0, then this is just raised to the 0th power. This is just p choose 0, so it's always going to be 1. So we can get started right away. The first thing I'm going to do is find my coefficients, okay? So, and remember we call those c sub k's, right? We use that terminology for, or that notation for the coefficients. So then c sub 0, okay, would correspond to that very first coefficient, which is the first term, which is just 1, okay? So nothing surprising there. It's that term right there. Okay, c sub 1, okay, so this would be 1/2 because you know what, I failed to say that this function that they gave you can be rewritten as 1 plus x raised to the 1/2 power. So your p-value here, I'll label it. This is your p-value right here. That is a p. I'm trying to write a p. This is your p-value, okay, 1/2. So going back to the coefficients, c sub 1 would be 1/2, choose 1, okay? So this k right here is 1, standing representing the first degree. Okay, so because k is 1, we're on this term right here, so then it'll just be 1/2 with your p-value times x. Okay, so 1/2 x. Or actually, we're just getting the coefficients at the moment, so I don't have to write the x value yet. Okay, I'm just getting the coefficients. Okay, c sub 2. Notice that your k value is 2, so this is 1/2. Choose 2. Okay, so then this is 1/2, and I'm following this definition, everybody, that since I'm here, k is 2, my numerator will have two factors, your power times your power minus 1. So in this case, since your power is 1/2, it'll be 1/2 times 1/2 minus 1, which is negative 1/2. Okay, all over 2 factorial. Okay, so then this is negative 1/4 over 2. Sorry for writing sloppily here. 1/4 over 2. So then this is negative 1/8. So negative 1/8 is that third coefficient. Okay. All right. We got one more to do. C sub 3. So C sub 3. Notice that your k value is 3. So this is 1/2. Choose 3. So the numerator then would be 1/2. And then there's going to be 3 factors in this numerator, right? 3 factors. The denominator is 3 factorial. It'll be 1/2 minus 1, which is negative 1/2. And then it'll be 1/2 minus 2, which is, what is that? Negative 1/2, so negative 3/2. Again, what I just did right there, folks, is I'm using this right here. So it'll be 1/2 times 1/2 minus 1, that's the negative 1/2 that I wrote, and then 1/2 minus 2, which is negative 3/2. So that's how I got that coefficient there. So anyway, all of this would equal 1/16. So I have all of my coefficients, okay? So then I'm ready to write down my answer, to be honest. So then it is 1 plus 1/2, this is x to the first power, minus, because the next coefficient is negative, and now it's x squared, and then plus 1/16, and then x cubed. The next term, we don't need to find any more terms because they said just find the first 4 terms, but if you wanted to keep going, the next term would be minus, right? Because you see the pattern, and then etc. Okay, but these are the first 4 terms of the binomial series for that function centered at 0. Now, I want us to see how good this series works for us as far as getting an approximation. Let's use this series that we just found, okay, to approximate something. So let's approximate the square root of 1.15. Okay, first of all, notice that this expression here is equivalent to the square root of 1 plus 0.15. So now it's in the form of our function, right? Remember our function was the square root of 1 plus x, and so what I'm going to be plugging into my series here is this value 0.15. Okay, now we did this in an earlier lesson. We did the following: p sub 0 at 0.15. That is your your Taylor polynomial of degree 0 is just this term, everybody. Ignore all the rest because p sub 0 means the Taylor polynomial degree 0. So anyway, you're only using this function right here. So you're ignoring the rest, just look here. So then this is p sub 0. So p sub 0 of 0.15 is just equal to 1. Okay, moving on. P sub 1, your Taylor polynomial of degree 1. So that means you're looking at just these two terms here, everybody. Okay, so basically it'll be 1 plus 1/2. Let me write 1/2 as a decimal just so that I don't have fractions and decimals. So 0.5 times 0.15. That is a 0 there, 0.15. This is 1.075. Look at p sub 2 of 0.15. So then it'll be 1 plus 0.5 times 0.15. Okay, that's p sub 1. And then minus 1/8 times 0.15 squared. This is equal to, well, approximately equal to, I'm going to round, 1.07218. Let me move 1 second here. Okay, 0.721875. Look at that. And then p sub 3, this will be the Taylor polynomial of degree 3, which is that all the first four terms that we just generated. So plugging in 0.15 into all of this. It'll be all of what we just wrote plus that cubic term. So 1 plus, see if I can write it all, 0.5 times 0.15 minus 1/8 times 0.15 squared, and then plus 1/16 times 0.15 cubed. Now watch this. This is approximately equal to 1.072398438. I want you to compare p sub 2 and p sub 3. They agree all the way up to 1.072. So what is that? 3 decimal places, and they agree. You know what I mean? So they agree to up to 3 decimal places. So the approximation is pretty accurate up to 3 decimal places. This approximation here, 1.07, we would say 1.072 is accurate up to 3 decimal places. I'd like us to practice one more time just to really get a strong grip on this idea. So let's do it one more time. In this example, we have this function. Okay, this is a brand new example. Okay, so f of x is equal to the cube root of 1 plus x. Okay, so remember this is equivalent to 1 plus x raised to the power of 1/3. So you see your p value is 1/3. See, in algebra, we never let that power be a non-integer value, a non-whole number like this. This is a rational number, and so we, in algebra, limited what the power could be. Here, we're just letting the p value be any real number, not 0. Let's do the same thing as we did before. Let's find the first 4 terms of the binomial series for this function centered at, let's center it at 0. Okay, so I suggest that we collect all of our coefficients first. All right, so c sub 0, right, is that very first coefficient. It's going to be 1 every single time, but it is your p value, 1/3, choose 0, but then this is just 1. Okay, we already knew that. All right, c sub 1 would be the coefficient of that second term, the coefficient of your first degree term. 1/3, choose 1. Okay, so then this is just 1/3 only one term in the numerator because this k value is 1. So just one term up there over 1 factorial. So this is just 1/3. Okay, easy enough. Let me just divide this to be organized. C sub 2, this stands for or represents the coefficient of that third term of your series. This is the coefficient of your second degree term. So basically your quadratic term. All right, so because your k value is 2, that means you'll have 2 factors in the numerator. So they will be your p-value, which is 1/3, times 1/3 minus 1 over 2 factorial. So then this is 1/3. Sorry, that is a 3 there. Make it look like a 3. Is that better? Not really. Oh my goodness. All right. Can I write a 3? Okay, that's going to have to do. All right, so 1/3, and then 1/3 minus 1 is negative 2/3. A much better 3. All of this over 2. So this number here is negative 1/9. Negative 1/9. So negative 1/9 is that coefficient that we mentioned. Let's go get our last one, okay? So C sub 3. Again, this represents the coefficient of your cubic term, okay, which is the coefficient of the fourth term of the series. All right, so your k value is 3, right? This is your k value. That means you'll have 3 terms in the numerator. So 1/3 times 1/3 minus 1 times 1/3, 1/3 minus 2. And then all of this over 3 factorial, which is 6. Okay, so if you do all this arithmetic, you get the coefficient 5/81. Now that we know all of our coefficients, we can write down our series rather quickly, rather easily. 1 plus, remember our second coefficient is 1/3 and x to the first power, and then minus 1/9, and then now we're at x squared, and then plus 5/81, and now we're at x cubed. The next term would be minus, and then so forth, etc. Okay, but again, we don't have to worry about those terms because they just asked us to find the first 4 terms.